Welcome to my video on HL chemistry, structure 3.2 for mass, infrared, HNMR spectroscopy, and isomers. This is our table of contents. Let's get into it. So starting off with cis and trans isomers. Cis and trans isomers must have a double bond. This is a key criteria. This double bond prevents it from rotating freely, therefore allowing it to be an isomer. The structure is like this, where you have two double bonded Cs with two sets of groups. And for cis isomers, that means the same group must be on the same side of a reference plane, and a reference plane is just the line that goes through the double bond, like this. Let's use hydrogen and chlorine. So a cis isomer would look something like this, where you have chlorine on the same, or you have hydrogen on the same side of the reference plane and chlorine on the same side of the reference plane. For trans isomers, however, it's quite the opposite. You still have the same structure like this, the double bonded Cs with two sets of groups. However, the groups are on opposite sides, opposite corners of the reference plane. So we would have a Cl here, an H here, and an H here, as such. And for something not to be cis-trans isomers, they can't have the same groups on the same right side. For example, they can't have the C having like H's on like this. This is no-go. Okay, so let's do this past paper question. Which compound shows cis-trans isomerism? Well, starting off right off the bat, we can tell that this C is double bonded with this C, and you have two groups, H and methyl group. But on the right side, you have two chlorine groups. Therefore, it's both the chlorine groups are on the same side, like this, with the double bonded C. Therefore, this is not cis-trans isomerism. Same thing with this one. You have two hydrogens on the same side, so it's not cis-trans isomerism. Okay, now let's look at this. We do have a double bond here. Reference plane is here. Okay, we have carbon here, CH2 here, CH2 here, and a chlorine. Well, this means that this would be cis isomerism. And let's just check D to be safe. This also has Cl and Cl on the same side of the reference plane. However, this is a single bond. And remember, we must have double bond. So, no. Bye-bye. So therefore, this is our cis-trans isomer. So let's talk about optical isomers. Well, first we have to understand chiral carbons. Chiral carbons are basically where you have a carbon with four distinct bonds. And each of these bonds have different groups. So a chiral carbon cannot have a double bond basically, because that would limit it to three bond regions. You would have one double bond and two single bonds. And therefore it would not be a chiral carbon. A chiral carbon must have four distinct bonds. Okay? So let's say this is a carboxyl. This is a CH2 and the rest of the molecule. This is H and this is chlorine. So this would be a chiral carbon because we have chlorine, hydrogen, carboxyl, and we have a CH2 plus rest of the molecule. Therefore, we label it as with an asterisk because this is what represents it as a chiral carbon. So now let's draw out this as a isomer. So we have carbon in the middle, chlorine, CH2, rest of the molecule, and a full black triangle means it's coming out of the paper. And a dotted one means it's going behind the plane of the paper, like this. And let's draw it along this mirror axis. Well, in this case, we can see that from carboxyl to the rest of the molecule, it's counterclockwise. But if we mirror it along this axis, rest of the molecule. It's important to note that you would want to draw what's first that's connected directly to the bond. So you wouldn't do rest of the molecule and then CH2. Here, now let's look at this side. They're all the same molecular formula. However, just the orientation is different. Now this is clockwise from carboxyl to CH2 and the rest of the molecule, different from this one. And that's what makes these optical isomers. Okay, now here's the question you guys have been thinking. What if you have more than one chiral carbon? Well, if you have more than one chiral carbon, then things would be a little bit more tricky. For example, let's draw 2,3-dibromobutane. So butane with 4 carbons as the spine, and 2,3, so we have a bromo here and a bromo here. And the rest of these labeled with hydrogens. Okay, let's look for chiral carbons. This one, I can rule it out because you have 3 H's, not distinct. This one, we have an H, a methyl, a bromine, and the rest of the molecule. So yes, this would be chiral. Now let's look at this one. You would have bromine, H, methyl, rest of the molecule. Same. This is chiral. This one, no. So you have 2 chiral carbons here. Now, how would you find the number of enantiomers you can make with a number n of chiral carbons? Well, let's derive this. So for 1 chiral carbon, we made one optical isomers, or a pair of optical isomers, I guess. So that's 2 enantiomers. Remember, enantiomer is a single one, so that's 2. So we can write it as 2 to the power of n, where n is the number of optical isomers. Because remember, if we have only one chiral carbon, then it's just 2. Okay, for in this case, that means that we have 2 to the power of 2. That means we have 4 possible enantiomers that we can create. And you must be thinking, what is the whole purpose of these enantiomers? Well, in mixtures, they polarize light differently. Some things that most likely won't be tested but are on the curriculum, as quoted by Miss Kittleson. Some mixtures are basically used to polarize light, and these optical isomers are used in that process. And I think the things you need to know is positive enantiomer is just clockwise, so plus enantiomer. I don't know how to spell it. I'm sorry. Okay, apologies if this is wrong. But a positive enantiomer is just clockwise, and a negative enantiomer is just counterclockwise. And a racemic mixture, like mixture of these enantiomers is basically 50-50 of positive and negative enantiomers. So therefore they would cancel out. That's basically it, but this is very surface level since it's not too important. Let's do some past papers. So let's start with that one. How many optical isomers exist? Well, we can use a formula of 2 to the power of n, where we derived it earlier. N is the number of chiral carbons. So let's start off by finding the number of chiral carbons here. Well, I can eliminate this one because we have H2, meaning that it has a single bond H and another single bond H. Therefore, there's no 4 distinct bonds. We can eliminate this one, and this one, because remember, we can't have double bonds. This one is a chiral carbon because you have an H, CH2, OH, OH, and the rest of this chaos. So therefore, it is 4 distinct bonds. Now for this one, remember we have an invisible H here. So an H, this chaos, and this chaos, but this way's clockwise, and this chaos counterclockwise. And we consider these two distinct because if we went this ways, we encounter this O, oxygen, first. However, if we went this ways, we encounter this this OH first. So therefore, we consider them distinct. So therefore, this is also a chiral carbon. Now we have 2 chiral carbons, so 2 to the power of 2, 4. Answer is B. Okay, now for this one. We gotta make a structure, an isomer structure for this that exhibits optical isomerism. So remember, we must have a chiral carbon. Okay, so let's draw out our spine. Remember, ene is double bond. So instead of putting it here, which would eliminate these two, let's put it here. So it would only eliminate these two, because edge carbons are less likely to be chiral carbons, because they might have. There's a high likely chance that they have repeating H's. So, so this is not chiral. This is not chiral. This could be chiral. This most likely not. So let's put the Cl here, so we don't have an H on this and H on here. So H like this, and then we can fill it with H. Okay, 1, 2, 3, 4, 5, 6, 7. Okay, so we have 7 H's, 1, 2, 3, 4, 4 C's, and 1 Cl. And then let's check for chiral carbon. We have a methyl, CH2, an H, and a Cl. Therefore, it has 4 distinct bonds. Therefore, this is how we do it. Okay, now for mass spectroscopy. Well, mass spectroscopy, it works by firing an electron and ionizing an electron from the compound, and therefore it becomes a +1 charged cation. And this cation is more unstable, so it fragments into many different parts, and that's what the mass spectrum detects. Okay, so the mass spectrum detects the cations that are left, and the things that are gone, or the ones that we're trying to find, are neutral atoms. So the greatest mass is going to be our molar mass for this one right here at 46. And if you see this like little signal here, just ignore it. It's due to isotopes. And then the mass difference is what we're trying to find. So for example, if you want to find what was lost to give it a mass of this, which is difference is final minus initial, 15. And that corresponds to a methyl group. So a methyl group was lost in order to get to this. And speaking of, at mass of 31, we have the relative intensity of 100. So relative intensity means that all of these intensities are based on this one. So if this is 100, then this would be, say, 30% of how abundant this one is. So the greatest intensity is going to be your most common fragment. So therefore, CH3 is the most easily lost or broken apart fragment. Now let's do a little past paper. So we need to find what G is, and we're given the spectrum. So here our molar mass is 60. And we have 45, so we have a difference of 15, a difference of 17, and a difference of 45. And looking at table, I think it was 19. No, not 19. Table 22 on your data booklet, you can find the corresponding neutral fragment lost. So 15 is CH3, 17 it's OH, and 45 it's COOH. And the molar masses of these are 15, 45, and 17. So clearly, these two added together is 60. Therefore, our answer is COOH, CH3, which is ethanoic acid. So that's our G. Now for infrared spectroscopy. First off, infrared spectroscopy measures functional groups and bonds in a compound, and it does this by emitting infrared waves and exciting these bonds and functional groups, and it measures how much they vibrate. And the downside of this is that it can't detect the location of them. It can detect its presence, but not the location. And it's also necessary to say that anything under 1,000 is generally considered less accurate because of noise. It's most likely most of it is noise. The things we are interested in is the peaks of this spectrum. And the thing I find quite ambiguous is that a lot of these peaks correspond to multiple functional groups, so it's very hard to actually be certain. But if you can go by this rule of repeats is most likely present. So say we have a repeat here of, say, carboxylic acid, another repeat of carboxylic acid, then you can know that carboxylic acid is most likely present. So yeah. And another thing to say is in the table 20 for infrared data, there's also a there's also a separate column that says intensity. And what it means by broad, or like how wide it is basically this part. Like if it's wide, then it's high, very broad. If it's like very skinny, then it's not broad. And for strength, it's how far it goes down. So I mean, this one would be more strong than this one. Yeah, okay. So you just look at the wavelength and correspond it to the type of organic molecule and bond. Let's try this one. So usually because of the ambiguity, the question will give you some sort of criteria or something to let you eliminate out the rest. It should. Okay, let's try this one. So we have to find the bond at X, Y, and Z. given of this compound. Okay, well, I mean, at X we have around 3600, Y we have around 1750, Z we have around 1200. So at X, we can see that it's probably going to be OH group. That's the only one that reaches 3600. At Y, it's going to be 1750, so most likely C double bond O. But here, this is where it gets a little more tricky, because at 1200, it could be this one or this one. 1200 fits in both ranges. So how do you decide? Well, you have to use what the question gives you. So for example, we have this molecular formula, and clearly that has no fluorine, or yeah, no fluorine, no halogens at all. So instead of CF, it must be CO. Must be CO. There. Now for H&OR spectroscopy. For starters, I think it's important to visualize each compound as having groups. So this would be a group, this would be a group, this would be a group. And this makes it a lot easier to visualize what's happening in the H&OR spectrum. So H&OR spectrometers, they use radio waves to detect hydrogens and adjacent hydrogens within each group. And they do this by emitting radio waves and measuring how these hydrogens in each corresponding group absorb and subsequently re-emit these radio waves. And so each group would correspond to a signal, or each set of symmetric groups would correspond to a signal. And I'll get into that later. But so for this table, group A corresponds to one signal, group B corresponds to another signal. And as you can tell, this red part is the signal, and the blue squiggly line is the relative integration trace. And this tells us the relative number of hydrogens between the two groups. So for A, we have a trace of 2, and there's indeed 2 hydrogens. And for B, we have 3, so there's 3 hydrogens. And this is just relative, so it could very well be 4 and 6. So be aware. And what I was saying earlier is that if you have 2 symmetric groups, well, not really symmetric in the sense of a typical, like, conventional symmetry, but more of special type of symmetry. So not symmetry as in like polar versus nonpolar, but symmetry as in the groups must have the same contents and also be connected to the same thing. So it can't be connected to another CH group. It needs to be connected to the same CH group. So for these two groups, we have 3 plus 3, so a total of 6 hydrogens. Therefore, we have an integration trace of 6. And both of these count for this signal. Now for group B, we have just 1 hydrogen, so just 1. And we use the ppm, which is what's on the x-axis, to determine and relate the shifts, or ppm, to the structure. Now it's time for high-resolution H&OR spectroscopy. Before, that was low resolution. Now we're doing high resolution. So what is the difference? It's just that high resolution can detect how much hydrogens are in your adjacent groups. So this is called splitting. So let's look at this example here. So for group A, there's 3 hydrogens, and we have 3 hydrogens for the signal, but there's only 1 spike. Now for group B, there is 2 hydrogens, and 2 hydrogens indeed, but there's 3 spikes. And group C, we have 2 hydrogens, but we have even more spikes. And then group D, we have 3 hydrogens and 3 spikes. So what is the difference between the spikes? Well, the spikes tell us how many hydrogens are nearby, like the adjacent groups. So for group A, this O is the adjacent group. It has no hydrogens, therefore it has just 1 spike. Now for this one though, for group B, we have 2 adjacent hydrogens, so therefore it has 3 spikes. And for group C, we have 1, 2, 3, 4, 5. 5 adjacent hydrogens, so that we have 6 spikes. In group D, we have 2 adjacent hydrogens, so we have 3 spikes. So there's this pattern of n plus 1 splits, where n is the number of hydrogens that are adjacent. Here. Like for B, we have 2, so 2 plus 1 is 3, so 3 splits. And each, a single spike is singlet, 2 spikes is doublet, 3 spikes is triplet, 4 quartet, so on. And something I find really cool is that it's related to Pascal's triangle, like the intensities between the spikes. As you can tell, the middle ones are more intense. And I think it's really cool because this is something from maths. How does it relate to chemistry? Well, I guess in high resolution H&OR spectrum it does. Like the relative intensities of the spikes, each spike goes along this. So if you have a singlet, it's just 1. Doublet, you have 2 equal ones. Triplet, you have 1, which is double the intensity of the ones on the edges, and so on. This is Pascal's triangle. Okay, now let's try some past paper questions. So again, with this spectrum, there's some ambiguity because a single ppm can correspond to many. So you got to use the context of the question and your intuition and a little bit of trial and error to figure it out. So let's look at our spectrum. So we have 0.9 and a 1.4 ppm signal. This has at least 5 spikes, or at least 5 splits, so it's going to be 4 more adjacent hydrogens. This has 3, so 2 adjacent hydrogens. And at 0.9, we can have CH3. That's the only one. And at 1.4, we can have CH2 and ROH. Okay, so like I said, it can correspond to many, so you got to use the context of the question. And looking at our question choices, everything's prop, so we have a carbon backbone of 3. That means that one of these have to encompass 2 groups, meaning these 2 groups are symmetric. And the only way for that to happen is the outer 2 groups are symmetric, because these 2 can't be symmetric. These 2 can't be symmetric. It must be this one and this one. So these 2 are the same thing. So therefore, this one of these is our symmetric, or encompasses 2 symmetric groups. And looking at the number of adjacent hydrogens, it must be this one that encompasses these 2, because by adjacent it would mean only this one. And since 2 is less than 4 or more, 4 plus, then that means that it's most rational, most logical to take that the adjacent group for these 2 is going to be this one. So this has 2 hydrogens, C. And that would match up because here, at 1.4, we have CH2, and that would work. Now, at 0.9, it's just CH3, and we know that these 2 are symmetric. So CH3 here, CH3 here. And looking at our CH2, it has 4 or more adjacent hydrogens, and that would definitely work because it has 6 adjacent hydrogens. So this would be our final compound, and that would be propane. So the answer is A.